Chapter 19, Chemical Thermodynamics. Once again, from this point on, in AP Chem, we kind of hit the apex where we got to buffer solutions and titration. From this point on, we're going to go down a really, like, AP Chem might have been something like this, going like this. But right now, the next two chapters are going to go like this really quickly. It's going to be downhill. It's going to be downhill quickly. Thermodynamics is a really easy concept, not difficult. As we go through the notes, you're going to be like, this is pretty obvious, this makes sense. Really easy stuff. So we should be able to easily finish this up maybe in 3 days and be done with it. And you'll know everything you need to know about thermodynamics, and it's a pretty easy process. Even when it comes to some of the calculations you're going to do, you're going to already know how to do these calculations if you've already done them already. Nothing new, and those calculations you did already were easy. And the new calculations you're going to do are going to be easy as well. All right, so here we go. Let's dive right into the notes here. Basically, what we're going to end up seeing here is we're going to start looking at chemical and physical processes. And when it comes to chemical and physical processes, we're going to see that they're going to be under one of three scenarios. The process is going to either be said to be a spontaneous process. And if we look at a spontaneous process, it says a process that will occur without outside intervention. I'm going to show you exactly how this looks. And we'll come back to these terms and make sure that we understand exactly what each term is saying. Now keep in mind, if it's going to occur without outside intervention, then we're going to simply say the term thermodynamically favorable. Meaning that in this case, I didn't even do anything. The universe is like, hey, you know what? I'm going to let this thing happen because under thermodynamics, it's doing exactly what it should do. Now, we have a spontaneous process and we've got a non-spontaneous process. A non-spontaneous process needs outside intervention in order to get this thing to proceed, which means that this is non-thermodynamically favorable. It's not going to occur. Give you an example, easy example. I could say taking something such as this eraser right here. If I let go of it, hey, it's thermodynamically favorable that it's going down to lower potential energy. But watch this. I put the expo eraser right there, and will it elevate itself? No, that's not going to happen. That's not thermodynamically favorable in this case. If it's going to elevate itself, I'm going to have to pick it up and raise it up, and now, okay, look at it. That's non-spontaneous. And then we're going to have the last process, which is going to be an equilibrium. And when it comes to equilibrium, it goes back and forth at a constant temperature. And the reason why we say at a constant temperature, because if you change the temperature, then guess what's going to happen to the equilibrium? It's going to favor the forward or the reverse. And that's why we said for equilibriums, those constants are only good at that given temperature. And also what we're going to see is there's no change as far as entropy to the universe. That one we'll talk about a little bit later on. So let's look at some examples here. Once again, downhill. And the reason why it's downhill, because the first example we'll look at is going to be downhill. So what we got here? We got, hey, AP chemists, I love thermodynamically favorable rise. It's like free energy. And we're going to see later on this chapter, some of you have taken AP biology. Did you ever learn about Gibbs free energy? Okay, well, that's okay. You're going to learn about it in this classroom. Because this is technically like free energy. If I take somebody that have them already sitting right here, that's just like free energy. Like, I can go down here. So if I look at this, I can say absolutely, this is a spontaneous process. I don't have to do anything. This skateboarder is going to go right down that hill and then go down to lower potential energy. No outside intervention needed. Hey, that skateboarder going down the hill, that's thermodynamically favorable. But at the same time, if I look at this example right here, hey, Mr. Hurlston, can you provide me some outside intervention to get me up the hill? This is non-spontaneous in this case. It's not thermodynamically favorable because once again, he is not, or actually it's not he, she is not going to get up this hill without somebody pushing and putting energy in to get her up that hill. And then we got this example right here. We got a skateboarder here. And literally, right before this class, I went in and I put this in here because I was like, wait a second, I got, an AP physics student in here, and if I don't put that in there, she's like, wait a second, no, Mr. Elson, this is not gonna happen. But if we assume there's no friction, and I let this young lady go, then what she's gonna do is she's gonna go down, come up, go down, come up, go down, and she's gonna keep on going back and forth, back and forth. And once again, when it comes to chemical reactions, we are going to have to say at constant temperature in this case. All right. Hey, I forgot I animated this thing. And actually, I did. I got this from, anybody remember this thing? We might have seen this. You might have seen it in conceptual physics or in physics. It's actually from the FET videos. Yes. Exactly. That's it. All right. So if we look at it, I got a waterfall that's sitting right here. One of the things I can look at with the waterfall is I know that right now, where the water is kind of being held back, that of course, I don't need to do anything. The water is going to spontaneously go from high potential energy down to low potential energy. I can say it's spontaneous, in this case, maybe going downwards. So it's spontaneous going downwards. Going down, going down. Hey, it's thermodynamically favorable in this case. But watch something that's really cool. If it's spontaneous in one direction, guess what it's going to be in the other direction? Non-spontaneous. Just like I said, hey, dropping the expo marker, spontaneous. Well, it returning back up there is non-spontaneous. The same thing is be true here. It's spontaneous going down, but it's non-spontaneous going in the opposite direction in this case. So thermodynamically favorable going down, non-thermodynamically favorable going upwards. We'll see that for chemical or physical process. We'll see the exact same thing playing out for physical processes as well. All right, next thing we got going on here. Absolutely. We said that once again, that when it comes to these processes, that they're going to be directional in this case. Spontaneous in one direction, but once again, if it's spontaneous in one direction, it's going to be non-spontaneous in the other direction, non-thermodynamically favorable in this case. So once again, going from low potential to high potential energy, non-spontaneous. Even if we look at it from the standpoint of chemical reactions, we see the same thing play out. If I have a nail that's sitting right here, I know if I leave that nail exposed to the atmosphere, that it is going to go through a spontaneous process of forming rust in this case. But at the same time, I know even though it's spontaneous in this direction, which means it's thermodynamically favorable, that rusty nail is not about to go back and becomes a shiny nail just sitting there. Now, if I have some outside intervention, maybe I take sandpaper and sand all that rust out, I might get back to some of the exposed nail, but once again, non-spontaneous. If you look at it from a physical process right here, I've got two vessels that are here. I got A and B. Vessel A is empty, vessel B has some gas in it, 1 atm. Of course, if I open the spigot here, then this thing at high concentration will diffuse over here to this side at low concentration. And eventually you're going to get an equal concentration of two gases in the two vessels. Spontaneous, as soon as I do that, it's shooting over there. But what I can guarantee you is even though it's spontaneous this way, or thermodynamically favorable, going in the other direction where all this gas is going to push itself over to one side, I might as well use it. Ain't going to happen. So we'll use that verb, or that non-English word there. But clearly, I would have to push it in. So clearly, once again, things are directional. Easy, spontaneous, non-spontaneous. And once again, this we already talked about with the actual rusty nail. We said that once again, things that are spontaneous in one direction, which are thermodynamically favorable, are going to end up in this case, once again, being non-spontaneous in the other direction. And also, one thing to point out is that when it comes to spontaneous things, we use, in this case, arrows to signify that, hey, this thing happens to be spontaneous. And that's why we look at this reaction right here. I can say this reaction is spontaneous in this direction right here. But if it's spontaneous in this direction, then what I can guarantee you is if I flip this equation around, what was shown to be thermodynamically favorable, going in the other direction, once again, is going to end up being non-thermodynamically favorable in this case. And that's what you'll see by me flipping the equation around. It goes this way, but not going this way right here. All right. And then once again, we kind of saw this example right here that I already explained to you where we said that, hey, it's spontaneous going here. We're splitting the two vessels, given an equal amount. But once again, non-spontaneous going in the other direction. Simple and easy. Now, one of the things I do want to talk about is I want to talk about process with regards to temperature. What we're going to find out is that sometimes temperature is going to determine whether something is going to be spontaneous, thermodynamically favorable, or whether it's going to be non-spontaneous, which is non-thermodynamically favorable. And if you look at it, the picture that I have right here, I've got my ice that's sitting right here. And it says, hey, ice is going to turn from the solids into the liquid so long as the temperature is greater than 0 degrees Celsius. That is spontaneous. It will go and absolutely melt. We know it will melt. But what I can guarantee you is if you're going to sit there and have a temperature greater than 0, and you expect for this thing to freeze and go back in the other direction, you're going to be waiting there forever in this case because it's never going to happen. So I can clearly see that, yes, it's spontaneous above, non-spontaneous below. Thermodynamically favorable in this direction, non-thermodynamically favorable here. But watch what's going to happen here. We said, hey, if the temperature is greater than 0, hey, it's going this way right here, 0 degrees Celsius. But at the same time, if I do want it to be spontaneous in the other direction, then all I gotta simply say is that if the temperature is below 0, then it's gonna be spontaneously gonna freeze in this case. But below 0, it's gonna be non-spontaneous the other way. It's not gonna turn back into a liquid if it's below 0 degrees Celsius. So we're gonna see in a second as we start going through problems and so forth, that temperature can have a bearing on determining whether or not something is gonna be spontaneous, non-spontaneous way, but at the same time, I change the temperature. Now it's spontaneous the other direction, and non-spontaneous going in the other way. Pretty straightforward. So temperature can affect spontaneity in this case. And once again, we just talked about this. Hey, above 0 degrees Celsius, it's spontaneously going to melt. Below 0 degrees Celsius, it'll spontaneously freeze in this case. Easy enough. And skipping right ahead here. Now, what spontaneous does not mean. And spontaneous does not mean that something's going to occur at a really fast rate. To give you an example, if you look at diamonds, we know for a fact that diamonds will spontaneously convert themselves over to graphite. That is thermodynamically favorable. We can do the calculation, and eventually we will calculate. We'll look at a reaction, we'll plug numbers in, and we'll say, hey, that absolutely is going to occur. But if you're going to sit there and wait for your lifetime or my lifetime, it's not going to happen. I mean, we're talking about millions of years before this thing is going to eventually turn itself to completely nothing more than graphite. So when they say that diamonds are forever, that's not right. Diamonds will eventually go to something that's more thermodynamically favorable, which is graphite. Now, if we want to talk about the speed at which something is going to occur, then we want to talk about something known as chemical, what is it? Chemical what? It's chemical something. The speed at which a reaction is going to take place is going to be chemical, we learned it earlier. Hey, how fast these things proceed. First order, second order. Chemical starts with a K. Kinetics. We're talking about chemical kinetics. Chemical kinetics looks at the rate. Remember, it's how fast are the concentrations we lost per time in this case. So if we look at chemical kinetics, it tells us speed. This doesn't tell us anything about speed. Only thing it says is that, hey, it will be spontaneous in one direction, non-spontaneous in the other direction. Or we're at some sort of equilibrium in this case. And that's what we're looking at right here. A reversible process. We said spontaneous process will have arrows for the reactions. They're just spontaneous going in that direction and only in that direction. But reversible reactions, we're going to once again use our reversible sign here. And remember, the equilibrium is always going to end up being an equilibrium so long as we keep temperature constant. Because one of the things that we learned earlier is if I look at this particular reaction, And if I do something such as, I think it might be, actually I think it's an endothermic reaction. If you remember, at constant temperature, this thing is going back and forth, back and forth, back and forth. But here goes a question for you. What if I was to actually raise the temperature on this equilibrium? Would it favor the forward or would it favor the reverse in this case? So if I increase the temperature, would it favor going the forward or the reverse? And the forward. Because I'm putting more energy in. It's like, hey, I gotta take whatever you're doing and get rid of it and force the thing to go in the forward. And if it's proceeding in the forward direction, well, that's not an equilibrium in that case. So when we have an equilibrium, it has to be at constant temperature to allow this thing just to go back and forth, back and forth, back and forth in this case. And once again, no change in the universe with entropy. I'll come back and explain that because we haven't defined what entropy happens to be. So if we look for reversible processes, once again, you're kind of looking for that double-headed arrow to kind of give you the implication that, hey, this thing is going back and forth, so long as I'm not playing around with the temperature here. So on the next slide, and once again, reversible reactions, we don't say that they're spontaneous or non-spontaneous. It's its own class. It's just going to be, once again, reversible. Because we said if it's spontaneous, we can't use that symbol. We got to use an arrow in this case. So these are just some examples of reversible processes. And if you look at these different reversible processes, we have things such as a dynamic equilibrium. That's going way back. And we're talking about, hey, if you put a liquid inside a closed container, and we'll stop here, I guess. All right, so we'll pick up here tomorrow. And then tomorrow we'll be running through. I'll probably get, easily past the halfway mark. Probably about maybe 3/4 of this chapter will be done. Then we'll go one more day and we'll be done with this chapter, and then we'll move on to the last and final chapter, which again